In our integrated design project, we did a simple ammonia production plant where it is produced via a Haber Bosch process. This integrated design project requires us to implement both principles of chemical engineering and fluid mechanics. In PCE, we build a process flow diagram and apply mass and energy balance using conservation of mass, conservation of energy, reaction stoichiometry, and reactor conversion. Meanwhile, in fluid mechanics, we cover the sizing of the piping system, calculate the pressure losses both for major from friction and minor from fittings, using Reynolds number and flow velocity plus the delivery strategy to the storage.
Hello everyone, I'm Nushuhada binti Rosli, and I'm going to explain the process flow for the industrial ammonia production. The chosen route is the catalytic Haber-Bosch process. Fresh synthetic gas containing nitrogen and hydrogen in a stoichiometric ratio enters stream S1 at atmospheric conditions, which is 1 bar and 25 degrees Celsius. The gas is pressurized up to 200 bar through a multi-stage compression before entering the reaction loop. Looking at our process flow diagram, there is 3 key steps in our process flow, and one of it is compression and mixing. Fresh feed S1 is compressed to 200 bar S2 and combined in a mixer with our recycled stream R1. Next step is preheating and reaction. The mixed stream S3 enters the heater and rising the temperature from 25 degrees Celsius up to 400 degrees Celsius, which is the operating reaction temperature. In the catalytic reactor, exothermic synthesis takes place and producing ammonia. Next, we have cooling and separation. The hot reactor, effluent at 450 degrees Celsius, passes through a cooler and drops the temperature point to 25 degrees Celsius. Because ammonia has a higher condensation point compared to nitrogen and hydrogen, it drops out in liquid form, where the vapor fraction is 0 in the gas-liquid separator. And the liquid stream S8, contained with 97% ammonia, is then pumped to the storage. Now, the most crucial component of the loop is this recycled stream R1. As we can see in the table data that the reacted effluent S5 still contains unreacted hydrogen and nitrogen. So instead of wasting these unreacted reactants, we recycle back into the mixture as stream R1. This recycled stream maximizes overall plant conversion efficiency, drastically reduces raw material waste, and lowers operating costs. Next, I'll be explaining the function of unit operations that we have been used for our process flow diagram. Firstly, we use compression to increase the pressure from feed stream S1 1 bar up to 200 bar at the stream S2. Secondly, we use mixture to mix the pressurized feed stream S2 with the unreacted recycled material R1 to ensure continuous feed utilization. Next, we use heater to preheat the combined feed gas S3 from room temperature 25 degrees Celsius up to reaction temperature 400 degrees Celsius S4 for catalyst activation. And then we have reactor, which is where the main reaction occurs to produce ammonia and to recycle unreacted reactants and mix with the feed. And then we have cooler or condenser to convert ammonia into liquid state and lowers the temperature from 450 degrees Celsius to 25 degrees Celsius at the stream at 6. For the separator, we use it to separate two-phase mixture into liquid products and unreacted gases, which is nitrogen and hydrogen for recycling. Lastly, we have pump to maintain pressure and move liquid ammonia product from stream S8 to stream S9 to the storage.
Moving on to the second part, we perform a mass balance on the reactor to determine the inlet and outlet molar flow rates. For the hand calculation, several assumptions are made. First, the process is assumed to operate at steady state with a single pass nitrogen conversion of 20%. In addition, an ideal separator is assumed for the hand calculation, while the simulation employs a two-phase separator. Therefore, slight differences between the calculated and simulated stream flow rates are expected. Because the overall process operates at steady state with zero overall accumulation, this means that in overall mass balance where the input of the reactant is this and the output is 0, the reactor's net consumption must be equal to the specific feed input. Based on this, exactly 25 kmol per hour of nitrogen and 75 kmol per hour of hydrogen are consumed in the single-pass reaction. We use a table to simplify our work. To calculate the total reactor inlet, we applied the process specification of a 20% single-pass conversion. Since only 20% of the incoming reactants are consumed, we can back calculate to find the total feed entering the reactor, which allows us to complete the remaining outlet flows using mass balance. The same is done for other substances. For the energy balance, steady-state operation is assumed. Changes in kinetic and potential energy are neglected, and no shaft work is performed. Hence, the general open system energy balance simplifies to the enthalpy balance shown. We have obtained the molar flow rate for each component, so we need to find the specific enthalpies using a reference state of 25 degrees Celsius and 1 atm. For instance, nitrogen's heat of formation is 0, and its sensible heat change at 400 degrees Celsius is 11.15 kJ per mole based on the appendix table B.1. Applying this methodology across all components, we calculated a total reactor enthalpy change of this value, which shows the exothermic nature of the synthesis.
Now I will be presenting the mass balance and energy balance for the non-reactive unit, which is a compressor. Before performing the calculations, we make several assumptions. First, the compressor operates at a steady state, meaning there is no accumulation of mass inside the compressor. Second, no chemical reaction occurs, so the composition of the gas remains unchanged. Third, there is only one inlet and one outlet, with no stream splitting or mixing. We also assume that only pressure changes while the gas composition remains constant. Because the number of unknowns equals the number of independent equations, the degree of freedom is zero, which means the system is solvable. This diagram shows the compression process. The inlet stream S1 contains 100 kilomole per hour of a synthetic gas. The gas consists of 75% hydrogen and 25% nitrogen at 1 bar, 25 degrees Celsius. Inside the compressor, the gas compressed from 1 bar to 200 bar. At the outlet S2, the total flow rate and the gas composition remain exactly the same. The only significant change is increase in pressure. For the mass balance, flow in equals flow out. Since there is no reaction, the inlet and outlet flow rate are identical. Hydrogen remains at 75 kilomole per hour, while nitrogen remains at 25 kilomole per hour, and therefore the total flow rate is still 100 kilomole per hour. This confirms that the compressor only increases pressure without changing the amount of the material. Next is the mass flow rate calculation. Using the molecular weights of hydrogen and nitrogen, we calculate the mass flow rate of each component. Hydrogen contributes approximately 151.2 kilograms per hour, while nitrogen contributes about 700.5 kilograms per hour. Adding both together gives a total mass flow rate of approximately 851.7 kilograms per hour. This value is conserved because there is no reaction occurring in the compressor. Now let's move to the energy balance. The compressor is assumed to operate at a steady state. Change in kinetic and potential energy are considered negligible. Heat transfer occurs only through the compressor wall. The gas behaves as an ideal gas, and the compression process is assumed to be reversible and isothermal. Under these assumptions, the energy balance equation simplifies it to change in enthalpy equals heat transfer plus shaft work. For an ideal gas, enthalpy depends only on temperature. Since the compression process is isothermal, the inlet and outlet temperature are both 298.15 Kelvin. Because the temperature does not change, the enthalpy also remains unchanged, and therefore the enthalpy change is 0 kilojoule per hour. Even though the enthalpy doesn't change, the compressor still requires energy to compress the gas. Using the reversible isothermal compression equation, the required shaft torque is calculated as 1.313 times 10 power to negative 10 power to 6 kilojoules per hour. This positive value means that external work must be supplied to increase the gas pressure from 1 bar to 200 bars. From the energy balance equation, since the enthalpy change is 0, the heat transfer must balance the shaft work. The calculated heat transfer is negative 1.313 times 10 power to 6 kilojoules per hour. And the negative sign means that the heat is removed from the compressor during compression. This helps maintain the gas at a constant temperature throughout the process.
Moving directly into Chapter 3.1, our focus shifts to the practical engineering of fluid mechanics and piping design for our ammonia production plant. Our primary objective here is to ensure the safe, reliable, and efficient transport of high-pressure process fluid across our pipeline network, with S3 stream serving as our main design example. Operating at 200 bar and 450 degrees Celsius, our synthesis loop requires rigorous material selection. We specified ASTM A335 grade P22 seamless alloy steel for its high temperature strength. Crucially, grade P22 prevents hydrogen embrittlement. We applied a standard commercial steel roughness, which is 0.045 millimeters. At 200 bar, standard Schedule 40 pipes fails required safety margins due to its thin walls. We selected Schedule 160 to withstand severe hoop stress and provide essential corrosion and erosion allowances. Our model is anchored by 3 core assumptions. First, steady state flow, assuming fully developed flow, leaving transient surges to control system. Second is thermal boundaries, assuming near isothermal or adiabatic behavior for short segments. And third, velocity heuristics, targeting 10 to 30 meters per second to balance pressure drops and capital cost.
I will be presenting the pipeline sizing and the pressure drop specification and go through step by step on how we arrive at this number. First, using the parameter obtained from the simulation, we determine the average molecular weight and the density of the fluid, then combine with the total mass flow to get the volumetric flow rate. Next, cross-sectional area was then calculated. In this case, we are using the sample calculation for stream S3. The Q was then divided by the area calculated earlier to get the fluid velocity. Using the fluid properties, diameter, and velocity, Reynolds number was calculated to confirm the nature of the flow. Then it was used into the friction factor equation. Lastly, we use friction factor, pipe length, and fitting losses to plug into the equation to obtain the total pressure drop. The step-by-step calculation earlier was then applied to all candidate size and yielded the following trade-off. The 2-inch pipe was selected as it has optimal fluid velocity and fairly efficient pressure drop.
Our final product, liquid ammonia stream S9, travels from the separator at 200 bar down to a storage tank at 18 bar. Using the extended Bernoulli equation, we accounted for friction head, elevation head, and pressure head. Friction losses across pipeline P7 and P at total is 6.06 kilopascals in a globe valve throttles that access separator pressure safely. Our final product, liquid ammonia. Assuming a conservative 10-meter elevation rise, elevation head comes to 58.86 kilopascal, giving a total pump head of 64.92 kilopascals. That's an ideal hydraulic power of 25.5 watts, and at 70% pump efficiency, our actual pump power is just 36.4 watts. Tiny since ammonia is dense and our flow rate is small. Since our product exits at 25 degrees Celsius, pressurized ambient storage made more sense than refrigeration. Ammonia's vapor pressure at that temperature is about 10 bar, so we designed for 18 bar for a safety margin. Our production rate of 848.74 kilograms per hour gives 20,370 kilograms a day. With a 7-day storage buffer, that's 142,590 kilograms or 237.65 cubic meter net volume. Capping the field at 85% per API standard 2510 scales that up to 279.58 cubic meter gross. Using a standard 4:1 length to diameter ratio, we get a 4.46 meter diameter and 17.84 meter length, rounded to our final spec, a 4.5 by 18 meter bullet tank holding 286 cubic meter.
Finally, we have come to the conclusion of our integrated design project, which is we are able to showcase the application of principal chemical engineering, including mass and energy balance on the reactor for reactive units and condenser for the non-reactive units for optimizing ammonia production. Secondly, we are able to apply fluid mechanics for optimizing pipeline design through pressure drop analysis, pump power estimation, and storage tank design. Also, using Reynolds number, Bernoulli's and the Darcy-Weisbach equation, and Reicher's safety for handling and storage, all demonstrating the integration of theory with practical solution. Lastly, for feature enhancements such as incorporating process automation, heat integration, and advanced safety measurement can be further improved the efficiency, sustainability, and the cost effectiveness of the ammonia production process. That's all from our group. Thank you.